Hey everybody, Blake Veneer here again with another part in this series titled Spacetime Particles, where we are hoping to use an Aether model to solve some of the unresolved issues in physics, such as dark matter. This particular part, we're going to start to actually look at what the framework would need in order to be successful. So we're going to start with talking about uh, a criteria, some initial criterias and checks that I have used to kind of verify or vet, not necessarily vet, but just some starting blocks for determining if a model has potential or not. Um, and then we're going to talk about some of the initial restrictions that we're going to place on this model. And then from there, we are going to start to work out satisfying Newton's first law, which I had discussed in the previous part as being one of our biggest hurdles with an Aether model. So let's get started. And so first, a lot of experiments have been set up in the past or have been run, and they have basically told us that an Aether model is impossible. I'm going to basically kind of turn that around a little bit, and I'm going to just double down on an Aether model. I think we've kind of run into a dead end with other theories in our previous approaches. And so when there is an experiment that says that an Aether model is not possible, I am going to instead think of how we can update the Aether model so that it can still be successful. So basically, we're just committing to this Aether model, and we're going to make sure that we can update the Aether model to match the physics and not necessarily abandon it until we are, there's no hope left. But for now, we're going to commit to this Aether model idea. And there's a lot of, over the years, been thinking about physics for a long time. And I've noticed in the last 5 years or so, a lot of my progress is made by first moving back on on my conceptions and notions of physics and what everybody has said. So what we are going to do is we're going to start from scratch. We're going to only add the minimum amount of stuff necessary to kind of create the behaviors that we're looking for, and then we'll add on from there. I don't want to start a model with certain conditions that might send us down the wrong path. And so, that being said, we'll come back to that a little bit later, but here is my kind of golden criteria when I'm kind of thinking about physics. So I've always wanted to try to understand what's going on with fundamental physics, and so I kind of have this series where I will first try to come up with a theory that makes the double slit possible, and this is like without any magic or like collapsing of the wave function or anything that's like seems spooky action at a distance, that kind of stuff. I personally believe that physics should make sense. It's not just, a lot of scientists or professors or whatever say that quantum mechanics is just never going to make sense, and I don't agree with that. And so we have the double slit experiment. I'd like to be able to explain that without any like crazy phenomenon. Exchange forces, those should all be mediated by something real. Now, that's not to say virtual particles aren't real, but we should be able to understand how that exchange is happening. It's not just some field. A field has to be made of something. And then for exchange forces, we need to be able to show how they can be repulsive and attractive. And it seems like repulsive is actually pretty easy to come up with ideas on. Attraction is quite a bit more difficult. Now, exchange forces would include electricity and magnetism and all those other forces. Gravity, has its own little test here, because I feel like gravity, I mean, doesn't necessarily follow the same kind of mold or the framework as the other forces. And so I like to treat that one different. And I also treat how gravity is going to behave with mass and light. That's not necessarily the same mechanism. So, um, gravity also kind of really is space time, and that type of test there. And then we have special relativity, and that would be just that all local physics should behave the same. And so when I'm trying to come up with an idea for, some sort of fundamental framework for how physics can work, I like to try to come up with an idea that makes the double slit work. Then once that works, I'll move over to the exchange forces. Then I might throw that previous idea out and just come up with one that works with exchange forces, and then move on to gravity. And I kind of just go through with, my idea, and work on each one of these one at a time, and then cycle through. And so any good, solid idea that has potential for being, explaining the fundamental physics should be able to answer all four of these. And we don't need to go towards any sort of crazy strings or anything more abstract than that to start, because, this is, these are kind of like important cornerstones of any theory. And if you start with something like strings, you're so deep in some theoretical guess that you don't know if you've made the wrong turn, many guesses ago. And so I like to start very high level, and we should work from the high level down into, something more fundamental. And, so I would have guessed, like, in my opinion, we should have tried to come up with a theory. And then as we try to add more conditions, we would, maybe approach a theory with strings, not come up with a theory with strings and try to match that to reality, because that is not going to be very successful, in my opinion. And so that's just one example, but maybe I'll talk more about this in another video. And so ultimately, where we are now with these space-time particles is, this is me having gone through a lot of this, and I personally think that this space-time particles Aether model is going to have the highest chance of being successful for a full theory at the moment. So now, initial restrictions, I'm going to basically have two, and that is going to be that the space-time particles communicate directly with adjacent space-time particles. So everything happens through an interaction that makes sense, and that's through adjacent interactions. And then I want to give the space-time particles mass. They're not necessarily going to be moving at light speed, and I think they'll actually be stationary a lot of the time. And so if you don't have mass, then you can't have momentum for a non-relativistic, like a non-speed of light particle. And so I personally think that mass would be important for being able to create interactions and other things like that. And then I don't know if this is a restriction or just a property, but I want to make sure that space-time particles can store all necessary information to establish necessary fields. And so now, as I said in the previous video, we had two main hurdles with an Aether model, and that is, first, we need to break Newton's first law, which is anything in motion will stay in motion. And the second one would be the second law of thermodynamics. The second law is more at the quantum level, so we are going to ignore that for now. But in order for some particle to move through a medium and not slow down, we have to figure out a way around Newton's first law. So if we have a ball in water, this is super basic, right? So we have a ball, and typically I'm going to draw the ball as stationary, and then there's going to be a flow with velocity this way. The flow is going to move. There might be eddies, you know, vortices in the back. We're going to get streamlines, stuff like this. So when the ball is moving through water, we're going to have friction and pressure drags. This would be our wake drag. So we're going to get all sorts of different things inhibiting the motion of the ball through the water. Now, our goal is to create something new that can get around this friction or pressure. So now, initially, a lot of people would say, no mass, no viscosity. However, we can't take the mass out, but maybe we can play with the viscosity here. So let's look at what viscosity does. So if we have high mu means that the ball is going to heavily drag the material around it. So if we have a velocity coming in here, then this is going to be a little arrow. Right, so imagine this is honey. And so as the ball, this is the velocity of the fluid. As the ball is as the fluid is moving around the ball, it's going to kind of stick to the ball. And so there's going to be this very gradual gradient of velocities from the ball. Now low, and so this would be high drag. Low. So now we do low mu. So low mu is going to have a much sharper transition. So at the surface of the ball, we have a boundary condition where the ball and the fluid are going to have the same velocity, which would be 0 if the ball is stationary. But very quickly, the fluid is going to match the bulk flow. And so this is going to have low drag. Okay, so if mu does not equal 0, then the drag does not equal 0. Now, I'm going to say that space-time, a particle, is made of space-time particles. And if a particle is made from space-time particles, at the boundary of the particle and just the regular space-time particles, there's always going to be some sort of interaction. And so at a minimum, there will be some viscosity or some non-zero viscosity. So we can't assume viscosity is always 0, right? Is not equal to 0. Or, yeah. Anyway, so with that being said, if viscosity is not equal to 0, but we need drag equal to 0, what do we do? Well, our main assumption is that things are smooth. Right? So this does not work if things are smooth and continuous. So what does a discontinuity do for us? And I'm going to argue that discontinuities are absolutely essential to this theory. So all of our math, when we're trying to do integrals, we like smooth and continuous functions because they evaluate very well. However, smooth and continuous functions lead to energy leaks and infinities, right? Because they kind of never end. You could have the slightest, just the little smallest bit of viscosity, and that's still going to add just a little bit of friction or something, and we're going to end up slowing things down. Or you could have, anytime there's just the slightest whatever, if it's smooth and continuous, that will be significant in the long run, especially if you're looking at time or distance. So, now what does a discontinuity do for us? Is it creates a barrier that can contain energy, and this is going to be very critical. And there's going to be a lot of places where we can use this little idea in order to create, stabilized locations of energy, help create this stabilized area where momentum is does not dissipate to the surrounding space-time particles or medium. So now, in order for this to work, we're going to introduce the idea of an inertial sphere. And so how does that look? We're going to have a particle, and then we're going to say that around this particle is some inertial sphere. Gosh, I was supposed to be a circle, but now, so V equals 0 here, V equals 0 here, and then we're going to have V out here. So around this particle, we have an inertial sphere, and that is going to drag all of the space-time particles with it. And then what's going to happen is there's going to be some sort of slip condition on the outside. So basically, let's do this. Whoa. Didn't mean to delete, but now I get a chance to do a better circle. Okay, so I wanted blue. So high mu. So in the inertial sphere, everything is basically going to be attached to the particle. So you're going to have a high viscosity at this boundary layer, low to 0. Right? So basically here, we're basically introducing this inertial sphere. And inertial spheres is not like, maybe the name is unique, but this is not like an idea that is never been come up with before. I'm just arguing that, inertial spheres have been made in the past basically to explain Michelson-Morley experiment. I'm saying that we need inertial spheres to deal with Newton's first law. And so how this would work here is some interesting. Let's look. So we have, let's just imagine that the particle P is at here. We have R going this way. This is distance away from the particle. And we have some sort of property. And I'm just calling it the mass influence property. And as you move away from the center of the particle, this mass influence is going to decrease. Okay. Now, this mass influence, it doesn't really matter what it is. It could be gravity or some sort of space-time distortion. But I'm just saying that there's going to be a property that is correlated to the proximity of the particle. And now as you, what I would say is that the higher the mass property, the lower, this is going to be V slip. So the higher the mass property, the mass influence property, the lower the potential slip condition is, or the slip velocity is. So as you move faster, you need to have a higher slip velocity. And so this actual inertial sphere would have to be pushed out to the right, would actually grow in size. Now, and yeah, one other thing here is that this shape here, I just drew a sphere, but this shape could maybe have like a, could look more like a teardrop. Who knows what this shape would be, but it would be perfectly shaped such that this slip condition is met for the entirety of this inertial sphere, or the boundary surface on the sphere. What is this? What does this look like for special relativity? Well, we'll just do super high level. I'm not doing any math here. We're just kind of musing or doing thought experiments. So, okay, so how does this look when we go faster? So we have our particle. We have our inertial sphere. We have our velocity here. Now, the key that we have to think about is that as we're moving fast, through a medium, we need to have the mass transfer from the front to the back right? This needs to be equal. So we always need to be able to move the same amount of mass from the front of this inertial sphere to the back. And so typically how this would happen is, let's say this, what color am I? This is just 0.3 C, whatever, it doesn't matter. Then this would be 0.6 C maybe, I don't know, right? But in order to effectively accelerate and move space-time particles, so this would be the mass of the space-time particles from the front to the back, we need to accelerate the flow. And this is just same as standard fluid dynamics. However, V must be less than C. And so that's kind of, we have this kind of limit here, which is going to cause problems for this theory. Because as we go faster, we're going to approach C, and then we're going to no longer be able to satisfy this condition unless we have a change of density. So free space density equals P. I'm just going to call it rho naught. And then this would be rho. And so if we have an increase in density, rho, in order to meet this condition, this mass flow rate, then we're going to have an interaction with this boundary. And it's not likely that we're going to have a difference in density over this boundary. So we're going to have rho here. So this would be front, this would be inside, maybe rho back. But all of these inside, right? So as we go faster, the density in this front area is going to increase in order to satisfy this mass flow equation. And so in order to keep this boundary stable, it is likely that the density inside the inertial sphere is going to look like it increases as well. Okay, so if we have an increase in density, the first question would be, isn't that going to change how the physics behaves? Because space-time is defined by these particles, right? So, okay, so does the density change in the inertial sphere change the physics? That's a great question, but we have to remember that the inertial sphere mass okay, so mass defines the inertial sphere. Space-time particles define, so distance is not defined by some unit of measurement like a meter, but distance is defined by the number of maybe space-time particles that you would traverse. And there's also no absolute reference to the size of a space-time particle, right? So if you have space-time particles at a higher density and you travel 10 units of those, that's going to appear to be the same distance for us as space-time particles with a lower density, while you still travel 10 units of space-time particles. And so going back to the mass is that mass is concentrated space-time particles. And so there's going to be a condition where density. I'm just like rho naught for just standard density of space-time. Right? If particles are made of space-time particles, then there's going to be a balance between the space-time particles, the density of them, and the internal pressures of the particle, right? So now if we say rho equals 2 times, then our particle is going to be smaller, right? But everything is going to be smaller. And so the physics should behave exactly the same. Now, this is going to probably reach some limit, but I'm assuming that for a bit, we can change the density of space-time particles and have the same physics. Eventually, that's probably going to reach a limit where things are going to start to behave differently. But I don't believe that space-time particles need to have any predefined size. They only care about the size relative to each other. And so basically we have two things, right? As the density increases, the size of the particle is going to decrease because there's higher pressures in the local area. But we're always going to have this reference frame of the particle that is the mass that's creating the inertial sphere. So essentially, most importantly, is the mass maybe stabilizes or normalizes now. This is going to be, oh geez, this is kind of the crux of the matter there. But yeah, so the mass creates the inertial sphere. We can increase the density of that inertial sphere, which then changes the absolute size of the particle or the mass, but the mass normalizes it all to kind of its own interactions. And so even though we would be in a higher density area, we would see it or experience it just as normal space-time. So then what does this do for the length contraction? Let's look at that. Sorry. So somebody might initially say, well, this is kind of, we have our particle, we have our inertial sphere, and then we're going to say rho not here, rho equals 2 rho not. Well, if we have higher density, and I just said that distance is not a measurement, but a matter of the number of space-time units that you might travel. If the density changes, then we would have, L parallel and L perpendicular would appear to be contracted. Now, right, so, right, because like essentially this would be 10 units, whereas this would be 10 units. And so the problem with Lorentz is that Lorentz is a matter of in parallel to velocity. Now, is this, and so basically here we're saying, well, now there's this perpendicular thing. And I'm saying don't get too caught up on trying to correlate the Lorentz contraction, which is a function of moving reference frames, and this is compressed inertial spheres. So they're not actually the same. They're two different two different phenomena that both happen. And so yeah, we are going to see some contraction or some apparent contraction. I'm gonna have to do some simulations with how light kind of moves around, and that might illuminate this a little bit more. But do not, I guess what I'm saying is, do not correlate increased density for a Lorentz contraction, because I do not believe that they are the same. They're two different things. Now, what does this look like for relativistic momentum? So as you go faster, you're going to pull along more space-time particles. So if we have one mass over here, maybe here, and so we'd say V equals 0.1 C, density equals, something, we'll just make some number, right? Density has increased a little bit. Now if we go here, velocity equals 0.5 c, rho equals, there's, 4, whatever. Oh, boy. Let's do this. So as we go faster, the density is going to increase, the size of the inertial sphere is going to increase, and so it is going to require more and more energy to accelerate this particle. If we were to slam into a wall, we have to remember that inside the inertial sphere, the viscosity of the spacetime particles relative to the particle itself is going to be very high. So as we collide with this target, all of the energy of the space-time particles moving in that inertial sphere are going to be added, or are going to help to force the particle forward or onward. And so therefore, as the particle collides with the target, we're going to get an additional energy or momentum from the moving inertial sphere into the particle. And so it's going to be as if the particle has way more mass and energy than in the classical case. Now, I don't know if this is going to make any sense, but I really sometimes struggle with how could Einstein have come up with an equation that so perfectly relates to something that's so different. Like, how can we have an equation for relativistic momentum that accounts for a moving inertial sphere when there really wasn't, that wasn't the initial goal or anything like that. But what we need to remember is the relativistic momentum derivation is something done out of necessity versus fundamental, like some idea. And what I'm saying there is how we generally calculate relativistic momentum is if we have some mass that's moving this way, and then we have a spring here, and this is going back and forth. So this mass is going to oscillate relative to the force of the spring in its initial conditions. If this is moving, then there's going to be time dilation, and so an outside observer is going to see that oscillation going slower. They're going to measure the same perpendicular, the same amplitude, but a lower period. And so the only way to make sense of the math, because the physics of this spring are not changing, it still has the same spring constant. In order to slow the period of oscillation down while keeping the spring force the same, or the spring constant the same, is we must increase the mass appropriately based off of the time dilation. So I don't know. Yeah, that's just a random thought that keeps me up at night, is that really relativistic momentum is a necessary, was calculated to make sense of these conditions. It wasn't necessarily created to, based off of some grander idea of how it comes about. Now, typically when somebody is talking about special relativity, they will talk about two space people, or space stick people without suits. And if there's going to be some velocity between them, some delta V. We have lots of different scenarios. V1 could be moving at 0. V2 could be equal to V. 1 could be going to V. 2 could be 0. Or some combination. But regardless, we don't know. It's, the argument is that you could never argue which one is actually right because it's all relative. And so the person 1 is always going to see person 2 moving towards them at velocity v, and so they're going to see person 2's clock moving slower. However, person 2 is going to see person 1 moving towards them, and they're going to see person 1's clock moving slower. And so that's all well and good. However, with this new theory of space-time particles, we have kind of a problem with that. And that is because now we have we have an inertial sphere. I don't know if I said this, but in a density that is not equal to, so I guess the density would be greater than P naught. Now, what does this look like? Well, you could do something neat here and say, what if density is related to the rate of like the flow of time? So, so that's kind of interesting here, because then you could also argue that, rho is going to be proportional to the gamma factor, gamma being one minus v squared over, or 1 minus v squared over c squared square root. And so as things go faster, your density increases, and then your time slows down. That's kind of neat. But again, you have an inertial sphere that is different than the other person's inertial sphere. So now it's not necessarily just perfectly relative or symmetric. This inertial sphere is going to be tied right? So this inertial sphere, depending on how big or small or whatever it is, it's going to be tied to the largest influence in your vicinity. So if there's a giant sun, and that's the closest thing to you, your inertial sphere is going to be moving through the inertial sphere of the sun, and this is going to be appropriately sized. If you're closer to the Earth, then it's going to be relative to the Earth, and then both you and Earth's inertial sphere is going to be relative to the sun. But how this looks going back and forth, now we have two different observers. We're going to have to do some simulations there, and so I'm going to kind of come back to this a little bit later. And we can kind of look at how the Lorentz contraction and how time dilation would be for a moving inertial sphere with different variable density. But yeah, we'll come back to this. This could be a little bit of a problem, or at least there'll be some interesting thoughts to come. So now, this is very high level, kind of hand wavy stuff, and I'm sorry for that. And it's mostly kind of just to establish some baselines here. Next, I want to kind of continue to, well, there's going to be two kind of issues, and I'm going to maybe go back and forth between those. But One, we'll use what I talked about today to kind of define, like develop a little bit more requirements and ideas uh, for how we're going to move forward. And then this other one is with this idea of space-time particles, some of the physics and our concepts are going to have to change a little bit. So we'll be kind of reviewing some of those. So these two will be done kind of back and forth. I do want to, once we've kind of got enough of the foundations sorted out, we will make a little bit of a relativistic checker or like simulation to kind of look at how things behave with an moving inertial sphere. And then eventually we will start to do some space-time particle simulations to start to basically, we'll simulate how forces and masses kind of distort the field or the flow of space-time particles around it. So anyway, we're going to be bouncing around a little bit, covering some interesting ideas in the next few videos. But thank you for watching. Please leave your comments and questions below, and I will continue to do this. And hopefully people find it interesting. If not, it's good for me to get all my thoughts sorted out. So thank you for your interest, and talk to you next time.